0 plus 1. Hello everyone. Welcome to IIT-JAM in Chemistry tutorial number 50, and this is lecture number 9 of the Physical Chemistry chapter Solid State. The subtopic of this lecture number 9 is close packing in metals and metal compounds. And in the first part of this lecture number 9, we are going to discuss metal structure. First of all, the first element of the periodic table, which is metal, is lithium. So we have to start our journey from lithium. So lithium is a metal. It undergoes metallic bond formation. So why it is a metal? And if it is a metal, then how it is a metal? So if you see the X-ray diffraction pattern of lithium, then it will be confirmed that here one lithium is surrounded by 8 other lithium atoms in its neighbor, close neighbor. So the structure, the lattice is actually BCC lattice, that is the body centered cubic lattice. And in other way, you can visualize this as two interpenetrating simple cubes. Okay, this blue colored simple cube interpenetrates this violet colored unit cell simple cube, and this way the apex, violet apex, becomes the body center of the blue unit cell. On the other hand, this blue apex becomes the body center of this violet unit cell. And this way, one atom is surrounded by 8 other nearest neighbors. This one is surrounded by, the blue one is surrounded by 8 violet ones. On the other hand, this violet one is surrounded by 8 blue ones. So this way, lithium undergoes a metallic structure. Now lithium, since it is number 3 in the periodic table, so it has the electronic configuration 1 is to 2 is 1. And it clearly indicates that it has one valence electron. This is 2s1 electron. By only one valence electron, covalent bonding is not possible with 8 other atoms, because in the XRD we have found that one is surrounded by 8 atoms. So covalent bond with 8 atoms is not possible. But the 2s, 2px, 2py, 2pz orbitals of other atoms are available. And these valence shells of the neighboring atoms are very close to each other's nucleus. As a result, what happens? This is the 2s1 electron of this lithium atom. Now it can move here, it can pair up with this one, or here to px, here to pz of the third one, or here to py of the fifth one, anywhere out of this vacant 2p orbitals or half-filled 2s orbitals, the electron can move. Therefore, the valence electron of lithium has complete freedom to move from one valence shell to the valence shells of the other atoms. As a result, the 2s1 electron is not localized in its own atom. What about the criteria of metals and metallic bond? If you look at the periodic table, then you will see that the metallic character actually increases from top to bottom. And also it increases from right to left. That means if you go from left to right, you will go towards the non-metals. Or if you go from bottom to top, you will go towards the non-metals. Now, this column is actually inert gases. So there is nothing about metal or non-metal. So the extreme right corner, fluorine is there. So this is the element which has highest non-metallic character. On the other hand, the extreme top left bottom corner, francium is situated, which should have the highest metallic character. So the left bottom cornered element, francium, has the highest metallic character. And on the other hand, you can also visualize this likewise, that electropositivity increases from top to bottom and from right to left. And metallic character is directly proportional to electropositivity. Now, criteria of metals and metallic bonds. So metals have some extra electrons beyond their stable valence shell or complete octet. Now see, lithium. Lithium has a stable valence shell, which is 1s2. Suppose sodium. Sodium has a stable octet, which is 2s2, 2p6. This way, magnesium also has a stable octet, that is 3s2, 3p6. So this way, metals have some extra, but beyond that, they have some extra electron, because lithium, the extra electron of lithium is 2s 1. The extra electron of sodium is 3s1, and the extra electron of potassium is 4s1. So these extra electrons can easily be made free by the metals. So these electrons are lost by these metals. So this way, these metal atoms become metal cations. As a result, the metal atoms become metal cations. Okay, these are the metal cations. These are also termed as the kernels, and these are the free electrons, freely moving electrons. The metal cations are sometimes termed as the kernels, as I have said already. And the matrix of metal cations is embedded in a sea of mobile electrons. So you can easily see here that these metallic cations are embedded within a huge sea of electrons. And the free electrons cement the metal cations, and a very strong force of attraction known as metallic bond results in. That means if you are building a wall, then between you are using brick, and between two bricks you are applying a cement sand uh, mixture. So this cement sand mixture, this roll of cement sand mixture is being played by these electrons here. So these two are the bricks and these are the cement sand mixture. Okay. So this way, electrons are cementing these two cations. And as a result, a very strong bond is resulting in, which is known as the metallic bond. Now, metallic bonds can be well explained with the help of molecular orbital theory, and the extended molecular orbital theory is known as the band theory. So, the theory of metallic bonding is well explained on the basis of band theory or extended metallic orbital theory. You can see these are the atomic orbitals, and these are the molecular orbitals. So, if you take two metals, two atoms, this one 2s1, this one 2s1, then the electrons will gather here. Now, if you take 3, then 2 here, third one here. If you take 4, then 2 here, and this upper non-antibonding orbitals, molecular orbitals, remain vacant. This way, if you take multiple atoms of this metal, then this half band is filled and this half band remains unfilled. So easily the electrons can move from this band to this band. And that's why these electrons become very much mobile, and metals can conduct heat and electricity due to this vacant band. So that is why it is known as the band theory. Simple. So the atoms of electropositive elements are thus bound with each other by chemical bonding, and this is a very strong type of chemical bond. The sea of free electrons, where the matrix of metal cations are embedded, are responsible for making the metals a good conductor of heat and electricity. Okay. Now, let us move on to the crystal structure, which is actually what about the close packing in a metal crystal? Okay, there are how many types, etc. So, metals usually crystallize in body centered cubic close packed structure, where the stacking is AB type of stacking. Like this is actually the structure of lithium, where two simple cubes interpenetrate in such a way that they become a body centered cubic close packed system. And the coordination number is 8. One kernel is surrounded by 8 kernels, or one motif is surrounded by 8 nearest neighbors. Okay, if this bottom layer is A, then body centered atoms forming the layer B. Again, this layer is repeated because this one has projection over this one. So this layer is being repeated here. So this is again A. So the stacking is AB type. And if you see the top view, the partial top view, then it will look like this. Look, if this is a square sheet, two-dimensional sheet, then the next two-dimensional square sheet actually is placed in the holes over the vacant side and forming um, octahedral holes this way. Yes, here octahedral holes are being formed, and that is why this one has 4 atoms in the bottom layer and 4 atoms in the above layer, making the coordination number 8. Now the next one is cubic close packed, which is actually the face centered cubic lattice arrangement. In the face-centered cubic lattice arrangement, you can see here overall 14 number of atoms. And out of this 14, 4 are inside the unit cell and 10 are outside the unit cell. But If you go to consider the layers, then you will find that this A is has projection here, and no projection in this layer, no projection in this layer. That means the stacking is A, B, C type of stacking. And here the coordination number is 12. Definitely it's 12. Because suppose if you take this one, it is surrounded by 1, 2, 3, and 4. Here also 1, 2, 3, and 4. In the above also there are 1, 2, 3, and 4. That means it has 12 um, atoms which are equally close to this one. So the coordination number is 12 here. And the last one is hexagonal close pact. Hexagonal close pact means the crystal system is hexagonal system. That means A equals to B not equals to C, alpha equals to beta equals to 90 degree, not equal to gamma, which is equal to 120 degree. So this is the hexagonal crystal system, and these are the body center of the any one of the prisms. Okay, if you divide this cuboid, then you will get a prism, and in alternate body center of alternate prism these atoms are situated. So the stacking should be AB type of stacking. Here also the coordination number is 12. Here this one is surrounded by 6 atoms in its equatorial position, and here in the bottom layer by 3 atoms, and in the above layer by 3 atoms. So overall 12 atoms again. Now this hexagonal close pact and this cubic close pact have packing efficiency 74%. That means void 26%. On the other hand, this one has a little bit less packing efficiency, which is 68%. So the void space is 32%. Now, this type of crystal structures, which metals have which type of crystal structure? I have a tabular uh, display here. So these metals have been tabulated here. So body-centered cubic close packed lithium, it is already discussed. Alpha iron means it is stable up to 912 degrees Celsius. Then delta iron is stable up to above 1538 degrees Celsius. Then niobium, chromium, tungsten, molybdenum, tantalum, sodium, potassium, barium, rubidium, cesium, europium, and vanadium. They all belong to body-centered cubic close pack. Then cubic close pack, that means face-centered cubes. Aluminium, gamma iron. Gamma iron means it is stable between 912 to 1538 degrees Celsius. Then silver, copper, gold, nickel, calcium, strontium, platinum, palladium, rhodium, and iridium. And finally, hexagonal close pack, zinc, alpha titanium, magnesium, cadmium, and zirconium. Okay, and by the way, for your information, let me tell you that hexagonal cubic close pact is anisotropic in nature, and it is more brittle than body-centered cubic and cubic close pact. So that's all about the first part of this lecture. Thank you and have a nice day.